Hello, everyone, and welcome to this edition of the Syneca webinar series, where today we have with us William Xiao from Simon Fraser University, who will present Making Cohort Data Fair. My name is Marta Lloret, and I'm involved in the Syneca project on behalf of MBLBI. I would like to make you aware that this webinar is being recorded, including the question and answer session at the end. And the recording will be available in the Syneca website and the Syneca YouTube channel. We have reserved some time at the end for questions from the audience. So if you have any questions, please write them in the questions box of the GoToWebinar application. I will briefly introduce you to the Syneca project. The Syneca stands for Common Infrastructure for National Cohorts in Europe, Canada, and Africa. It's a 4-year project funded by the European Union's Horizon 2020 program and the Canadian Institute of Health Research. Syneca's vision is to accelerate disease research and improve health by facilitating transcontinental human data exchange. To achieve this, Syneca works on several challenges. The first one is federated data discovery. So how, as a researcher, you can find cohort data of interest, and this could be for a particular genotype or phenotype, for example. And then once you find that data, how do you access it? So Syneca works on an interoperable authentication and authorization infrastructure. Once you access that data and want to ask questions across cohorts, there's a need for a harmonized cohort level metadata. And the ultimate aim of Syneca is to enable federated data analysis for research and healthcare applications. So Syneca works with a set of demonstrators in both research and clinical settings. And on top of all these challenges, there's a fundamental need for a transnational harmonized ELSI framework to address ethical, legal, and societal issues. In addition, Syneca has an outreach and training program to raise awareness and increase capacity building in these areas. Today's webinar is part of the How Fair Are You event, which consists of a webinar series and a hackathon, where we will share background knowledge and practical advice in order to facilitate the uptake of FAIR approaches. After this webinar, there are 4 more webinars on specific topics, such as the FAIR software tools, which will be the next one next week. And then at the end of April, we will run a hackathon, which will be a practical online event where we'll work on the implementation of FAIR principles in 3 parallel streams: cohort data, software, and training materials. If you want to know more about this event and register to it, you can check the information in the Syneca project website. Today's speaker, Dr. William Xiao, joined the Faculty of Health Sciences at Simon Fraser University as an associate professor in September 2020. He is also an affiliated scientist at the British Columbia Centre for Disease Control Public Health Laboratory and at Canada's Michael Smith Genome Sciences Centre. Prior to joining FHS, Dr. Xiao was the chief bioinformatician and a senior scientist at the BC CDC PHL for 8 years, and a clinical associate professor at the University of British Columbia. Dr. Xiao obtained his PhD in the Department of Molecular Biology and Biochemistry at Simon Fraser University, followed by a postdoctoral fellowship at the Institute for Genome Sciences at the University of Maryland School of Medicine. His research focused on microbial genomics and metagenomics. At the BC CDC PHL, he incorporated data science and knowledge engineering into his research and developed expertise in public health data sharing, integration, and harmonization. With experience conducting and applying genomics and data science research both in academia and in government laboratories, Dr. Xiao has developed a special perspective on integrating basic and applied research to improve our public health system. At this point, I will hand over to Dr. Xiao.
I guess good morning for me, but good afternoon in Vancouver, and good afternoon to most of you. So today I'm going to talk about how to make cohort data fair. And of course, you know, FAIR stands for findable, accessible, interoperable, and reusable. And because we introduced the concept last time around, I would not reintroduce the concept, but rather I would discuss how we can apply it to cohort studies. So cohort studies is essentially a study of a group of people who share a common characteristics or experience within a defined period. The cohort study are usually designed to be a cohort study usually is designed to be observational in nature, and it usually follows a large number of participants over a long period of time. The size of participants is needed because the outcome is usually not observed, especially in prospective studies. So a large number of participants usually is needed to have the proper power for making an observation. And it's usually carried over a period of time as well. Some cohort studies lasted for decades. It's useful when intervention type of studies, such as randomized control trials, cannot be performed due to ethical or logistic reasons. And exposure to risk factors are measured as outcomes of cohort studies. And one of the advantage of cohort studies is that multiple outcomes can be observed. So if you have, for example, a population level cohort or a large national cohort, usually you can stratify the cohorts to study different biological questions and observe multiple outcomes. So the overall process is valuable for scientific understanding of disease causations. And in Syneca, we have about 10 cohorts that are part of this consortium. And the goal of Syneca is to enable federated query and analysis of the varying and wide range of data set from the 10 different cohorts. One of the challenges with the cohorts, as I mentioned later, is that these cohorts have all been pre-established before the formation of Syneca. So in order to bring together the different cohort studies, the data harmonization approach is needed. And I'm part of the work package 3 focus on metadata harmonization, which would be part of my discussion today. So briefly, one would construct a cohort by first defining the study questions and scope and identify the study population and consent the individuals in the individual and participants in the study. Then first a baseline measure need to be established. So this is often through the use of various data collection instruments to measure or collect the exposure information to specific risk factors. So for example, if a study is interested in the effect of lean versus obese individuals, then weight, for example, baseline weight is established. And the group then, for example, is subclassified into different subgroup based on their weight. And essentially, the groups are divided based on whether they have or do not have the the risk factor or degrees of exposure as well. So degrees could be sort of binary or could be a gradient. So follow up with the participant at a regular interval to measure the outcomes using data collection instrument. That could be, for example, questionnaires, physical measures, cognitive measures, and biospecimen collection. So the individuals, participants have followed through the course of the cohort study. And as the data are collected, they're analyzed to see if the outcome correlate to risk factors, and using different criteria, then the causality of a disease, for example, is then inferred. So in Syneca, as I mentioned, we have about 10 different cohorts. I would just highlight a few that are sort of larger and more active as part of the work package 3. So the first is the Xiao cohort. It's a longitudinal birth cohort study of following approximately 3,000 families in Canada from birth to the age of about 8 years old. It's multidisciplinary in that it's not just studying one specific domain of science, but rather there's a collection ranging from environmental, psychological, genetics, genomics, and other disciplines, and large number of researchers with different backgrounds participate in the Xiao cohort study. It's a multi-model collection of data, meaning that as I mentioned, the use of various questionnaires, access to actual biological samples, in-home assessments, and clinical assessments were performed. And overall, there's over 300 different survey questionnaires being used in this study. The UK Biobank is another example of a very large-scale national cohort of about 500,000 participants from UK. And what's very interesting about the UK Biobank is that its data is accessible not just in UK but internationally, and also because the way the studies are set up to have such a high number of participants, it's also able to mobilize a subset of populations who, for example, were affected by COVID-19, and the study is able to be performed to link the host genetics to the disease status. And the third example is H3 Africa. It's a Pan-African consortium to build research program and infrastructures in genomic medicine on the African continent. And again, this is a international accessible cohort in terms of the data that's available. However, it also made the arrangement where study PIs in Africa get to retain a subset of data for their own studies to really enhance the capacity building effort in the African continent. And as I'll end today's talk with a bit of a discussion on the challenges associated with with open science and the effect that it might have in benefit sharing from the knowledge derived from science. I think the effort to have ownership and stakeholder rights within a Pan-African consortium can help solidify the practice of benefit sharing. Again, biospecimen and data collections for research are available. Okay, so due to the usually prospective nature and large sample size and longitudinal nature of cohort studies, these studies tend to be very expensive and labor intensive. And as you can imagine, if the data can be more fair and can be used for other purpose and can be reused by other researchers to answer secondary questions, then it would be more cost effective and have greater benefits. The second challenge is that data collection instruments and variables are usually specific to a study, and therefore the data may not be interoperable or machine readable. Indeed, that's one of the goals for Syneca, is to make the data more machine readable, so it could be queried using computer scripts. So the by and large, data are encoded as free text using customized pick lists, and also often the unit of measures are not always standardized, and the binning of data again is also arbitrary. So often different studies will have different ways of binning a spectrum of data into categorical information, or a scale of measures into categorical information. Another consideration is that most valuable data, especially ones concerning participants' medical records and other private information, personal information, is often the most valuable, but yet they're most sensitive and in most cases access controlled. And the fact they're access controlled and they're not machine readable also means often it's a long process to find out what data is available, how and whether it's relevant to the secondary studies that might be using such data sets. And the consent process may also be restrictive to allow the reuse of cohort data. More and more studies have starting to sort of acknowledge that broad consent is encouraged and needed in order to make the data more valuable and more useful. But broader consent also is not without criticism, especially if it's not done properly with proper information provided to the participants about what they're consenting to. And also, it's important that consents need to come with ability for the participants to withdraw from the studies at any time for any reason. So the discovery of cohort database content, as I mentioned, is a major challenge. Cohort profiles are often in descriptive texts that are human but not machine readable. So, for example, I copied a small section of the cohort profile from the Xiao study, and as you can see here, it has a lot of information about the time of the sample collection, the number of participants involved, the location of the participants, so on and so forth. But in such a paragraph, it's very difficult for a machine to extract pertinent information, and even the use of natural language processing and so on in such a context or such a paragraph may still most likely not able to extract the information and structure it properly in a way that's easy for machine queries to be made about the Xiao study. Similarly, data fields and data protocols are made openly available on Xiao websites and other cohort websites. However, again, they're usually in human readable formats. So for example, protocols is usually a PDF file, and data fields is usually an Excel spreadsheet. Again, not very conducive for data discovery. So in terms of access to data, here is an example of the protocols used for child studies to request data access. So in child study, there are 3 levels of access. So open access for essentially protocols and data collection instruments. There's the forms used and a list of the forms. And then there's registered access, which allow you to see, for example, the actual forms being used, but not the data collected. And it allows you to see some of the aggregated information, so summary stats for the various data sets. But the rich data, there's over 3 million data points in the child study. The rich data set, however, requires a fairly lengthy process to gain access. It involves submitting a study concept proposal that's reviewed by the child board, the child cohort study board, and various steps to achieve that is listed here. I won't go into the details, but also to highlight, even once you gain access to the data and carried out your analysis, at both the analysis and the publication stage, the data and the results need to be, the analysis and the results need to be vetted by the child study before it can be published. So doing so is really trying to make sure the patient, the participant privacies are protected, and that the studies are carried out correctly and properly, and proper interpretation of the child cohort data is done. But again, it's a fairly lengthy process, and it's certainly not open science, open access mode. So the minimum metadata for cohorts is needed in order to allow us to combine the different cohorts and to allow us to query across different cohorts. So the approach that's commonly used essentially is to come up with a metadata specification to describe the cohorts. So one example of such effort is the metadata for machines framework for the Go Fair consortium. And briefly, it's a process where community-specific metadata practice are reviewed by both the domain experts and by the data specification or metadata experts, so people who understand how to structure such information, and people who understand the biology or the science behind the data need to come together and construct the metadata elements, follow the FAIR principles, and you also need to then formulate these decisions in a machine actionable template. And this usually refers to specific file formats that are easily parsable by machines and can be queried. And then the last step is to register these templates so that they are discoverable and findable by machine APIs so the registration of that in some registry or is performed as the last step, and this results in a domain-specific community-built fair metadata schema. Okay. So an example of such is the minimum metadata model for Syneca that have been developed in the last little while and is still work in progress. While it's not quite following the necessary M4M template, the idea is very similar. So based on surveys of common data fields in the 10 cohort studies, and note that we only have access to the forms used to collect data and information about the studies, but have no access to the actual data. Again, this is usually access control. So even for us who are developing the metadata standards, do not automatically have access to the data in order to protect the participants. But through the process of collating the information across different cohorts and using the data dictionary provided, we're able to come up with a list of acceptable, a list of common fields and the acceptable or accepted data values. And this is supplemented with common data fields from additional data catalogs. There's about 30 or 40 of them used. And then supplement again with simulated user cases that are of interest by other Syneca work packages who want to perform specific queries on the data set. So each of the variables that so far there's about 80 of them is then grouped into broader categories such as socio-demographic information, economic characteristics, disease information, medication information, and lifestyle and behavior information. And this is structured based on the Maelstrom research data standard. The standard was picked because it's already used by several of the cohorts, and it's has a bit of a hierarchical structure to help organize the data. So we started with that in order to promote compatibility with existing data catalogs. And then to take it a step further, each of the variable then is mapped to ontology terms. And this is still work in progress, but ontology called GECO, which stands for Genomic Cohort Knowledge Ontology, has been developed. So here's an example of the structured variable in the minimum metadata model. So for example, within the biosample, there might be information about sample types and the actual values of the samples types and whether they're available in a particular cohort is captured through this hierarchy. And you can know that currently NCIT, which is a data dictionary or thesaurus is used to represent the term, but again, it's still work in progress, so I won't get into too much details right now. Now, so I talked about the findable and accessible challenges and also some potential solutions. I'm going to switch now to the interoperable and reusable components of the FAIR principles. So as I mentioned, because the metadata are not, or the data, sorry, across cohorts are always collect in the same format or the same standard. So harmonization across cohorts is needed. And okay, so here's an example of clinical data that's being collected for foodborne diseases. And you can see that the different forms all have information about sorry, this is the same one, but information about the about dates, about the subject, and about the food and the symptoms that they are that they have consuming the food. But the form used by in BC by BCCC and for example by the national lab or by WHO, on the other hand, are structured differently, and they have common elements but different granularity and different information. So that's one example. And another sort of more made-up example, but to show more clearly what the issues might be, is shown here. So for example, all four terms, specimen source, isolation, host tissue sampled, and source, are all referring to the same concept, or semantically they meant the same thing, meaning that they are about the specimen that are being isolated. However, another study may use the term source to refer to the data source or the sample source, in other words, which lab submitted the data or the sample. So the same term source is used in different contexts to have different meanings. So the use of these arbitrary labels then became a major issue in terms of data harmonization. Another example that's maybe more topical is the COVID-19 case report forms that are used in Canada. So my group performed a study that looked at all the forms used across Canada by the different provinces, and also the form that's used by the federal lab to collect information. And I'm just showing two examples two examples here, but the theme is universal in that almost all the jurisdictions collect similar or same information, but use different terms and use different granularity. So for example, the host health status, all of them, or except one, collect symptomatic and asymptomatic information. And almost all of them also note whether the subject is deceased or not. But in terms of more gradual information that has a gradient, such as patient being stable or have deteriorated, or a patient is deteriorating, then these more granular informations are not consistently collected. And the other common fields would be the gender information, and male and female are always noted, but for example, one territory uses M and F rather than male and females, and there are some jurisdictions have more information about the sort of non-traditional gender gender information, and include, or some of them include an unknown field, which is really should be the standard practice, given that sometimes the information is simply not available or not known or cannot be verified. So in short, like the inconsistency often are minor, but creates headache, especially for computers when trying to integrate the information. Here's one last example looking at genetic information regarding COVID-19 mutation. As many of you know, the variant of concerns are a major headline these days, and tracking the mutations in these variants and lead to a flurry of activities, both in publications, but also in non-traditional formats such as blogs and Twitter information. But as you can see by the example here, there's various ways of encoding simple information regarding whether a nucleotide or amino acid have changed. So I won't go through the details, but suffice to say is that they usually have the location information and the amino acid or nucleotides that are being substituted. But what's variable are the whether it's about whether the information is in nucleotide space or amino acid space. In other words, the location in the genome, and often the abbreviation used, such as deletion, is not standardized, and the name of the genes sometimes are specified and other times are not. So these, again, minor inconsistencies are readable to human and comprehensible by human, but when it comes to machine processing, these then becomes a challenge. So Maelstrom has a systematic way of harmonizing data, which I thought is worth quickly going through. So for basically for each of the data set, there's it's a step first to define the research. For each of the cohorts, there's a 5-step process. Step 0 is to define the research question, objective, and protocols. And you want to do this consistently across all the cohorts you want to harmonize. And then iteratively from step 1 and step 4, it's done for each of the cohorts. So you first assemble information and select the studies you want to include, and you define the variables and evaluate the harmonization potential of each of the data sets. And then the data is processed, and there are specific ways to transform the data that I won't get into, but usually it's a manual process. Rarely can you come up with automated rules or automated conversions for the data set without some manual human intervention. Step 4 is to estimate the quality of the harmonized data generated. So it's important to make sure that after the transformation, the information in the original data set is not lost or misrepresented in the harmonized data set. And once that's done for all the cohorts in consideration, then the harmonized data set is then disseminated, and the product, the data set made available for data consumers. And so Maelstrom, as I mentioned, has built up catalogs over the last 10, 15 years or so. And as I mentioned, our aim is to take it a step further and apply newer technologies such as semantic web and ontologies to further make the data more fair, if you can say that. So I'll just briefly define a semantic web refers to a set of standards and best practice for sharing data and the meaning or semantic of that data over the web by using applications. In other words, using computer applications. So semantic web can be processed directly or indirectly from machines. So in other words, it's both machine readable, but also importantly, it's human readable. So human and computers can work in cooperation. So ontologies are building blocks of semantic webs, and it's a way of structuring knowledge in a machine readable way with defined terms and relationships. And in ontology, one can provide a set of vocabulary that can be used to model a domain of knowledge, which is type of objects and concepts that exist in a specific area and the relationship between them. That's the definition of ontology. So practically speaking, ontology provides standard and linkable IDs for names of data, names for forms and tabular data fields, and also the values or terms for categorical variables. So the modeling process is to turn the data into a hierarchical structure. Maybe it's a subjective process, and that's one of the major challenges and major criticism for the use of ontology. Even though the process is, the mechanism is formalized, how the data is actually structured is still very much a subjective process. So, and so who is the model for, and how is the model going to be used, and what granularity is the models, are all issues that is still to be worked out, and by ontology experts and domain experts working together to represent their knowledge. So the use of upper level ontology may bring some harmonization. In other words, it provides a high level conceptual framework for the knowledge represented, but it still does not guarantee full interoperability. So even though I'm saying ontology is one solution, there's still a lot of areas, a lot of details to be worked out. Okay, so some recommendations from Barry Smith, who's an ontology expert on the ontology creation and reuse. So first, building ontology is a suite of interoperable modules structured to provide birth for further ontologies as needed. In other words, try to not create ontologies only for one use. And this also apply for data representation of cohort data. Again, think in terms of the interoperable modules, rather than just very narrowly in terms of the subject areas and the questions that you're trying to answer right away. And so this would improve the short half-life of your data. So the recommendation is to not to start with the data itself, because that can change rapidly, but with a conceptual model based on the entities, and based on entities could be a thing, could be a process, could be an attribute, and try to model the concept that the data are used to describe, rather than just the data themselves. And try to reuse existing ontologies rather than reinventing the wheel when possible. So there's some information on how to do that, but an example is the Oval Foundry suite of ontologies that allow people to reuse terms from a large number of domains. So Gecko, which is, I'll talk a bit more, is a ontology developed by Syneca to represent metadata of cohorts, and it has reused terms from Oval Foundries whenever possible. So the strengths of ontology is that it's a formal representation of object concepts and relationship among them, and it allows a shared understanding for communicating cohort information. And it overcomes the semantic heterogeneity of information by standardizing that and in an explicit format. Ontology are also interpretable by human and by computer. So the information integration using ontology, by using ontology, information integration, it can occur more harmoniously, because the sort of thought process that go into modeling the data help to improve the integration. Now, so the most important thing is that ontology is machine readable, and meaning that it also can be embedded into computer applications directly. So that makes the data representation aspect more transparent and more easily accessible. So mention briefly of a project called Genomic Epidemiology Entity Mart. We started this project to model and collect data for genomic epidemiology, but in reality, the same concept can be applicable to other domains. And the idea is quite simple, that ontological terms are best most valuable when reused and in such a way that it can then be used to link data sets. So the same, if two data sets are referring to the same concept, then computers can use that to infer the relationship between the data sets. So we created a platform where users can shop for ontological terms and use that to build a data specification, and therefore encourage term reuse and concept reuse. So I'll end with some challenges associated with harmonization. So it's always a balance between accepting only the precise uniform information, and therefore if some data sets don't fit that precise definition with precise granularity of information, then it's not included. But that limits the potential of integrating a large number of studies. The alternative is to accept a broader granular representation of the information and therefore incorporate more data sets. However, that may also lead to misrepresentation of the specific data sets when the data are aggregated. So, for example, broader terms that are used to aggregate more detailed terms can lead to the loss of details in the data. And as I also demonstrated before, the same terms can be used to describe different things, or more commonly, the same terms used to describe phenomena of different scales. So, for example, fever can be referring to temperatures that are 37.5 Celsius or above, or it could be referring to 40 Celsius or above. So that there's no standard labels for what a fever is referring to in terms of biological, in terms of the physical measures. Now, as I mentioned, I want to sort of start a discussion by posing this question. So making cohort data fair can mean broader and easier access to the data. However, usually only higher income countries who have more research capacities can take better advantage of such broader access of information than lower middle income countries that typically don't have the same research capacity to take advantage of the information. So the food for thought or the discussion point is, how can we protect the interest of study participants, especially ones from lower middle income countries, and enable benefit sharing while trying to make cohort study data more fair. Okay, so I'll stop there and I'll turn it over back to Marta.
Thank you, Will. Yeah, you can leave this slide up. So we open the floor for questions now. You can write your questions or comments about Will's question on the question box in the GoToWebinar application. We received a question during the registration process, so I'm going to start with that one, which says, do you think that making ethics committee approvals accessible and fair for clinical data collection is recommended?
Personally, I do think any study-related information, as long as it's not concerning individual level data, as much as possible should be made openly accessible, because that would help data consumers or other researchers to get a better understanding of the study and of the data that's available through the study. And this could include the ethics information, because that often does have details of the information being collected and how that information and what the risk of associated with those information being accessed, or the risk associated with the studies and so on. So they are valuable information in terms of trying to assess the content of the data set.
Okay, thank you, Will. I have also a question, which is regarding these data harmonization guidelines that you showed. In step 2, one of the things to do was evaluate the harmonization potential. Could you explain a bit more how you do that?
Sure. So this is related to whether the data sets are compatible or not, and mainly is looking at whether they share similar fields, and whether the fields are encoded in the way that can be integrated or can be aggregated. So give an example would be that would be easy to integrate would be if the temperatures are taken but in different units, then that's a field that's easily that's interoperable, because you just have to convert from Celsius to Fahrenheit, for example. But another example would be that might be slightly more difficult to harmonize, would be if for hospitalized patients, there might be degrees of sort of wellness, the sort of well-being of the patient in a hospital might be divided into different degrees from stable all the way to critical, or to even death. And that scale often is not standardized, but it's possible to somehow slot in the different descriptors based on the severity of the condition. So you can still fit it into the scale of stable and recovering to death, right? So it's somewhere between those two extremes that you can slot in the scale. But I'm trying to think of example where it will be very hard to harmonize. It could be that they make different assumptions. So for example, if the samples are collected in different ways, say one preserve the genetic material well, and the other, say, destroy the genetic material, then you might not be able to combine the availability of that particular sample, or even though both are collect blood samples, but one destroyed the genetic material in the process, the other preserved the genetic material. So even though both studies collect blood samples, they're not really compatible or integratable. So anyway, so there are strategies, I guess you could call it, that would help to harmonize fields. So these include if it's rule-based and as I mentioned, it can be transformed based on a formula or based on a set of rules, then that could be done automatically. Or if it's something that need to be conceptually mapped, such as the severity scale that I mentioned, that could also be done, but need to be done manually. So that makes harmonization more difficult. And but yeah, and as I mentioned, some of them, the fields are simply not the same or not compatible, even though both are about cohort studies. Or the COVID-19 example, some fields are simply not collected. So that makes a harmonization effort difficult because you have to make explicit note that this piece of information is not collected, or that additional values. Let's use the gender as an example. If you want to just include male, female, and unknown, but another data set has a few samples that's labeled with intersex, then do you just drop all those samples because you don't have the intersex value, or do you put intersex as unknown or intersex as male or female? So that's another example where simple concept but very difficult to harmonize because of the lack of information or the incompatibility of information.
Thank you very much, Will. It really sounds like a very challenging thing to do. But yeah, we are at the top of the hour now, so I think we'll leave it here. If you can show the last slide with the two next webinars.
Yeah.
So this How Fair Are You series continues with two other webinars, which is on Fair Software Tools next Wednesday. It will be 1 hour earlier than today. And then the week after, we have Practically Fair with Andrew Stubbs. So if you want to register for those, you can visit the Syneca project website. So thank you very much, everybody, for attending. And I hope we see you next time.
Great, thank you.